In this video, we're going to learn about teleoperation and how it applies to our robot. Just like we've got television, which is distant vision, and telephone, which is distant voice, teleoperation means distant operation or remote control. This is in contrast to autonomous operation, where we give the robot a task and it goes off and drives itself around and figures out how to do it. Although we generally want our robots to be autonomous, human control, being able to have an operator in the loop, is still an important part of robotics, especially during development and configuration. Teleoperation usually consists of two parts. Firstly, we need a way to send command signals, usually velocities, to the robot. And then secondly, we need a way to receive feedback from the robot to the operator, although this can be optional if you're going to be physically present with the robot while you're driving it around. We've already seen an example of teleoperation in action. In the last few videos, we've been using teleop-twist keyboard to drive our robot around and RViz to view the camera and LiDAR feeds that it sends back. But it doesn't take long to realise that using the keyboard for control is not very practical. You've only got very coarse control and you've got to keep the terminal window open and you're stuck sitting here at the dev machine. All in all, it's just not a very comfortable experience. So today, we're going to see how we can really improve that and make teleoperation a really good experience. The video is going to be split into 4 sections and you can use the chapters to jump to wherever you want to. So firstly, we're going to spend a good chunk of time looking at gamepads and how we can use them in ROS to drive our robot. Then we're going to look at RViz and other tools that we can use to receive feedback from the robot. Then we're going to look at how we can use a phone or a tablet to control our robot remotely with a video feed streamed to it. And then finally, I'm going to deal with a whole bunch of other little issues and tips and tricks that come up when we're doing teleoperation. Hi everyone, Editing Josh here. As I was putting this video together, I realized it was way too long. So everything that I say is later in the video will actually be coming soon in the next video as a part 2. Once that's out, I'll make sure I include a link in the description. The first step that most people are going to take to improve their teleop is to use a gamepad. And what's a gamepad? Well, it's one of these things. I'd usually call them a game controller, but I'm going to try and avoid using the word controller in this video because it's got connotations with ROS2 control and its controllers. ROS and Linux usually call all these kinds of devices joysticks, even though technically a joystick looks more like this. I'm going to chop and change a little bit between what I say. Most gamepads are going to fall into one of 3 main categories. We've got wired via a USB cable, wireless via a USB dongle, and wireless via Bluetooth. Each of these has their own pros and cons, and of course within each of these categories there's going to be a whole lot of different models with different features at different price points. And there's also going to be personal preference, so I prefer Xbox style controllers to PlayStation controllers. I just find them more comfortable. For most of this video, I'm going to be using this cheap wireless USB controller that I bought online. Now, don't get me wrong, this is not a good controller for a whole bunch of reasons, but it is cheap, it is wireless, and it works out of the box with ROS. So if you don't already have a controller that you want to use, then maybe you want to go pick that one up. Gamepads are great for robotics because they're already designed to direct something to move around. It's usually just a virtual something rather than a physical something. They've usually got a few buttons and a few axes, and it's more than enough to trigger whatever things your robot has to do. With ROS, we can decide whether we want to connect our gamepad directly to the robot or whether we want to connect it to our dev machine / base station and have it forward the control signals onto the robot. Connecting to the dev machine is kind of easier and it means we can swap between the sim robot and the real robot more easily, but connecting it directly to the robot itself is going to mean we have lower latency and less performance issues. There's nothing stopping you from setting up both, but for this video, I'm just going to set it up connected to the dev machine and forward the signals onto the robot. If you do want to do it the other way, just remember that the files I'm editing and the commands I'm running are going to have to be done on the Pi over SSH instead. Most people using ROS are going to be on Linux, and Linux has okay support for joysticks and gamepads, though not as good as Windows because Linux doesn't have quite as much a history of being game focused, although Valve is making great steps to change that. So our first step is going to be checking that our gamepad actually works in Linux. And it's worth understanding that the way Linux handles joysticks, there's kind of an old way and a new way. We're going to be focusing mostly on the new way for the rest of this video. It'll work fine for most circumstances, but I'll include some notes on the old way at the end just in case. Let's install some useful tools for working with gamepads. So I'm going to type sudo apt install joystick, jstest, gtk, and evtest. Then I'm going to plug the little USB dongle into the machine, turn on the controller. I'm going to run evtest, and it'll tell me that I needed to select the device event number for the controller, but it helpfully tells me that it's number 19. So I'm going to type 19, and now hopefully as I press buttons and move axes, we should see things going. So that's great. Linux is seeing my gamepad. You can also experiment with JS Test and JS Test GTK. They have a nice visual interface, but just be aware that that's actually using the old driver underneath, not the new event driver. Now that we know Linux can see our gamepad, we need to get it working in ROS. Now the normal way we work with joysticks in ROS is that we have a node that talks to the Linux drivers and publishes a topic of type sensor messages joy, which is pretty much just a list of the buttons and the axis values that we're pressing. Then other nodes can take these values and turn them into whatever they need. So you might want to trigger a certain behavior when you press a button, but what we'll be doing later in the video is we're going to be mapping the axes of the thumbsticks to a twist message, because you might remember twist is what we need to control our command velocity for our robot. So to listen to joysticks using the new Linux drivers, we use the joy package. So I'm going to type ROS2 run joy, and then you can see it's got two nodes. There's joy node and joy enumerate devices. So I'm just going to run that, and it's going to tell me, great, I can see a joystick of ID 0. So now I can type ROS2 run joy node, and by default it's going to connect, I've got the package there, joy node, and by default it is going to connect to the device with ID 0. So you can see it's opened the controller, and now I'm going to open a new tab here, and I type ROS2 topic echo / joy, and hopefully what we'll see is that as I press the buttons on the controller, that each time I press the button on the controller, it's going to be sending a message on the topic. If I just resize the window there, you can see that the axis values change as I move the sticks. This node has a few parameters. So if we type ROS2 param list, we can see some of the parameters that this node has, and we'll talk more about some of those a bit later. Now, something that I found this week as I was preparing this tutorial is that just echoing the joy topic isn't always that helpful, especially for things like figuring out the index of the button that you've pressed and that sort of thing. I had a quick look and I couldn't find any tools that seem to make this easier, so I've written one quickly. If someone knows that there's a better one out there, then let me know and I'll recommend that. Otherwise, I'll probably publish this one as a package. I might make some changes to it, but until then, I'll include a link in the description to how you can get it. So this is just a quick tool that I wrote this week. I've already cloned it into my workspace and built it. So I'm just gonna source my workspace, and then I'm gonna type ROS2 run joy tester test joy, and you can see it'll bring up this little window, and each time I press a button, it'll light up, and as I move the sticks, it'll tell me what value the stick is and show it on a little bar. So that just makes it easier. Now, something I'm going to quickly note down now is that the stick I want to use to drive my robot is this left thumbstick here. So that's axis 0 for left and right, and axis 1 for forwards and backwards. I'm also going to note down these top bumpers. We'll see why later, but I've got 6 is for my left bumper and 7 is for my right bumper, or L1 and R1 in PlayStation terms. Before we go any further, I'm actually going to create a launch file and a params file for our joystick. Now, the reason for that is the next node that we're going to run has a lot of nested parameters, and trying to type them in at the command line is going to be really annoying. So we're going to get the launch and params files up and going first, and then we'll add things to that. So I'll open up code. We'll start with the launch file, so I'll go ahead and create joystick.launch.py, and then I'm just going to paste in kind of a basic template that I've already got just to save typing it out. And all this is doing, you can see it's running the joy node that we ran a minute ago, and it's getting the params from a file called joystick.yaml in our config directory. So we better go ahead and create that. So we'll type joystick.yaml, and then in here we're going to have joy node, and then just like normal ROS parameters. Now, the parameters that we're going to set, we've got the device ID is 0. I'm actually going to be setting these just to what their default values are, but you might want to change them. That's why I'm putting them in here. The dead zone, talk about that later, but I'm going to set that to 0.05. The other thing you might want to change is the auto repeat rate. Oop. And that is set to 20 milliseconds by default. So now we can rebuild. So I'm going to kill this one, type :build, and now we should be able to type ROS2 launch the name of your package, so articubot1, and then joystick.launch.py. And hopefully, this is a classic. I've put an integer instead of a float. Happens every time. So we'll just run that again. This should be running exactly the same, so I should be able to run my little tester again. And we should see things coming through. Great, our launch file works. So now that we have our raw joystick data coming through on the joy topic, we need to turn it into a twist message to get sent to the robot. So the way we're going to do that is with a node that's called teleop twist joy. That's exactly what it does. It's going to take the joy message and publish a twist message. Now, teleop twist joy has a lot of parameters that we need to set. And so rather than run it at the command line, we're going to add them into this YAML file. But first, let's add it to the launch file. So I'm going to copy what we've done here with the joy node. I'm going to call it teleop node. The package is teleop twist joy. The executable name is teleop node. And then one other thing I'm going to do here is I'm actually going to name this node teleop node as well. The reason for that is the node name and the executable name don't line up for this one. That's not technically a problem, but it can just be a little bit confusing. So I'm going to explicitly name it teleop node, and then I'm going to pass in that same params file. Then make sure here down in our launch description, we run it as well. Now what I can do is in our YAML file, I can add a section for this node. So we'll go teleop node, and then ROS parameters. And now we've got to specify all the parameters for this. Remember that a twist message actually has 6 dimensions. It's got rotational and linear velocity on each axis, but our robot can only move in linear X and angular Z. So they're the ones we're going to need to specify. So we'll start with the axis linear for X, and we're saying which axis on our controller is that going to be? And you remember from before that that was axis 0. Then we've got scale linear. So scale linear is what speed we want it to move in X when we push that axis to its limit. For now, I'm just going to make that 0.5 meters per second. You can change that to whatever you need to. You can do that later, whatever. Then teleop twist joy actually has 2 modes. You can run it in regular speed and turbo mode. And that's quite handy for having moving your robot fast and then when you want some finer grained control. So we're also going to have scale linear turbo, and when we're in turbo mode, I'm going to set the speed reference to 1. Now we're going to have the same thing for angular, so I'm just going to copy and paste this whole block and change these to angular. And remember that these are going to be Z now instead of X because we're rotating around the X-axis, Z-axis. And then we want our Z to be axis 1, you recall from before. And again, this is now going to be 0.5 and 1 radians per second. You can adjust them if you need to. The next thing we've got to specify is which buttons we're going to press to enable regular mode and turbo mode. So I'm going to go enable button, and you remember that was my left bumper, which was button 6, I think. Oop. So 6, and enable turbo button was my right bumper, so that was button 7. And then lastly, this by default employs what's called a dead man switch. So that means if you let go of the buttons, the enable or the enable turbo button, then it's going to send a 0 speed reference and tell it to stop. And that's so that if you drop the controller and just bump the joystick, that sort of thing, that it's not going to send your robot flying. So we can disable that if we want. It is enabled by default, but I'm just going to explicitly enable it. So we're going to go require enable button and set that to true. So these are all the parameters for our teleop node. We're passing them in to the teleop node, and we're then going to run it at the same time as our joystick node. Let's see how that goes. Before we go any further, just a couple of mistakes I realized I made. I got the axes the wrong way around. Our X was meant to be 1 and our Z was 0, they were flipped. And then also, even though in the twist message, our angular ones are specified by the axis name, in teleop twist joy, this is called pitch roll and yaw, not Z. So with those fixed, I'm just going to go and rerun our joystick launch, and then I'm going to type ROS2 topic echo Command Vel. Now what we should see is when we move these, nothing happens. When I hold down the regular speed enable, these should move to plus or minus 0.5. And then when I hold down the turbo enable, they should move to plus or minus 1. Exactly what we want. Now that we're generating command velocities, we can try them out on the robot. Now, the safest thing to do here would be to test them in Gazebo first, then to test it with the robot propped up, and then test it on the ground, but I'm just going to go for it. So the first thing we need to do before we do that though, is you might remember that we need to remap the topic. Rather than being on Command Vel, it was on diffcont Command Vel unstamped. So I'm just going to type remappings, if I could spell, mappings is map from Command Vel to diffcont Command Vel unstamped. So I should remap that topic for us. So I'm going to go ahead and turn on my robot and SSH into it and launch the controllers just like we did in the last video. So moment of truth, I'm going to rerun our joystick launch so that we've got the remapping in there. And then I'm going to go ahead and I'm going to hold down the regular speed button and drive forward. Perfect, and backwards, and turn right, and turning left. So you can see that's quite slow. Let's try the higher speed one. Sure enough, I can drive it around and it's so much more natural than using the keyboard. There are some more little details around all this that we're going to get into at the end of the video, but before we do that, we're going to look at the other half of the teleop problem, and that's feedback. Now, there are a bunch of tools we can use to get feedback from our robot. The most obvious one to start with is RViz. It's not always the best one. There's some other tools out there that we will explore, but we're going to mostly focus on RViz. So I'm going to launch RViz with that config that we did in the earlier video. So launch that up. Now, the first thing that we're going to get from our robot as feedback is odometry. So I can almost not look at the robot and just drive it around purely based on what I can see on the screen here. So I can turn it around, drive forward, turn right, drive back the other way, that sort of thing. But without kind of any context of what's going on in the world, it's a bit hard, and I'm highly likely to drive it off the edge of this bench for the second time. The odometry is also very prone to drift, so it'll quickly become inaccurate unless we've got something else to give us a sense of space. The most natural type of feedback to get is, of course, the camera. Now, I'm still sorting out the issues with the camera here, but we can add an image display, not an interactive marker display. We can add an image display and specify our image topic. And of course, I need to run the camera driver first. So I'm just going to SSH in again and run the camera driver. All right, so that should be streaming the camera data now. So if I go image raw, we can see it there, and hopefully as I turn around, you can see the image moves. But you notice it's quite choppy, quite delayed, so if I stop, it's still going to keep going. And part of that is because the RViz version that is on Foxy doesn't have support for compressed images. Newer versions of RViz do, but in the meantime, we're just going to launch a separate program. So I'm going to run RQT image view, which is capable of displaying compressed images. And we should see that this is much more responsive. When I stop, it stops pretty quickly. If you're having trouble, you might want to try things like reducing the frame rate of the camera. We can do that with this driver now. I'll include some notes on that. But I've generally found that sometimes this really doesn't work very well, the image streaming over the Wi-Fi. And I think it's particularly if I'm in an area with a lot of signals. So if I'm doing this inside my house where there's lots of Wi-Fi bouncing around, I find that image stream really works very poorly. But here in the shed where there's no other Wi-Fi, it works great with no issues. So just be aware of that. The next thing, of course, we can use for feedback is the LiDAR. So I'm going to kill the camera driver and instead run the LiDAR driver. And again, if you were driving it around a room or a corridor of some sort, then you could probably use this LiDAR feedback as a pretty good way to navigate. So I can see that there's some kind of a wall over there, which is of course this. The LiDAR is not telling me that I'm on a table that I could fall off the edge of, but in general, I could use it to navigate. I can tell it's pointing at me now. This is me, this blob in front of it, that sort of thing. Now, you might find if you are having trouble with this, we can change things like the QoS policy in RViz. So We can change this to best effort, change the depth to 1. If you're having trouble, that might help it get the messages in time. Later on, once we start doing things like slam and having a map, we'll be able to see where the robot is within a predefined map of the room, and that'll be even better for navigation. So that's RViz, that's what we use a lot of the time, but I want to also talk briefly about 2 other tools that we can use to get feedback from the robot. The first one is a tool that I've written that will let you control the robot and get the camera feed and stuff to a phone or a tablet, and the other one is a tool called Foxglove. Editing Josh here again. As I mentioned earlier, I've decided to split the video in 2, and so the second half of the video, which has phone control and Foxglove and all the other fun tips and tricks, will be coming very soon in the next video, but I've kept the original outro. So that was a fairly comprehensive overview of teleoperation of our robot. So take some time, have some fun, drive it around like an RC car and see what you can do with it. Now that we've got teleoperation working, the next step is going to be automation. So in the next few videos, we're going to start looking at some of the more complex algorithms we can run with our robot. Things like SLAM using SLAM Toolbox, navigation with Nav2, and using our camera as an input for our robot to chase a moving target. As always, there's a link in the description to the discussion thread over on the Articulated Robotics community. So if you've got any questions or comments, make sure you head over there and join in the conversation. And these videos are only possible thanks to the support of my patrons on Patreon. So if you'd like to consider supporting, there's a link for that as well. All right, I'll see you next time.